Buffalo Harbor, autumn 1842. The air is thick with the smell of rotting wheat. A forest of masts stretched across the waterfront, ships locked in a gridlock that would last weeks. The Erie Canal had delivered on its promise. Grain from the interior now flooded eastward in quantities nobody had imagined possible. But the canal solved only half the problem. The wheat sat in ship holds, waiting. Stevedores, the dock workers who loaded and unloaded ships by hand, worked around the clock, their backs bent under 120-pound sacks, muscles straining against block and tackle systems that had not changed in centuries. The land could grow more than human hands could move. America had unlocked infinite harvest potential, but biology could not keep pace with physics. Something had to break the bottleneck. This is how grain stopped being a solid and started flowing like a liquid. The kinetic revolution that changed agriculture forever did not happen in the fields. It happened in the space between harvest and market. The antagonist was the shovel and the burlap sack. The numbers told the crisis in stark terms. By 1832, Buffalo's grain receipts had exploded to 2 million bushels. The Erie Canal had dropped shipping costs to a tenth of what wagon transport charged, but the savings evaporated at the waterfront. Unloading a single vessel took a week or more. Teams of stevedores descended into dark holds, shoveling grain into sacks, hoisting them by rope and pulley to the deck, then carrying them across gangplanks to waiting canal boats. Every bushel passed through human hands at least twice. Every transfer cost time, labor, and money. The economic threat was existential. The canal had made Buffalo the gateway between the Great Lakes and the eastern seaboard, but the port was drowning in its own success. Shipping rates had plummeted, but if it cost more to move grain across a wharf than it did to float it 300 miles, the entire system collapsed. This was the fundamental conflict, biology versus physics. The Midwest could produce grain faster than the human back could lift it. While Buffalo's waterfront groaned under the weight of 2 million bushels, the solution was already sitting in a dusty patent archive. 60 years earlier, a Delaware inventor had designed a machine that could move grain without human muscle. But the infrastructure to support it, steam power, industrial manufacturing, and the economic pressure of a genuine crisis did not exist yet. Soon, Buffalo's desperation would finally bring it to life. Newport, Delaware, in the 1780s. Oliver Evans stood in his flour mill watching water turn a wheel, watching that wheel turn gears, then watching those gears grind wheat into flour. The process worked, but it required constant human intervention. Workers hauling sacks upstairs, dumping grain into hoppers, and shoveling flour from one station to the next. He saw the mill as a single organism, a continuous system where gravity and mechanical advantage could replace muscle entirely. The Archimedes screw had lifted water for 2,000 years, a simple helical blade rotating inside a tube, pushing liquid upward with each turn. Evans adapted the principle for something nobody had tried before: dry goods. His screw conveyor sat horizontally in an enclosed trough, the rotating helix pushing grain forward rather than upward. No shoveling, no carrying, just continuous motion. For vertical movement, he invented the bucket elevator, an endless belt fitted with small cups that scooped grain from the bottom, carried it upward, then dumped it at the top by centrifugal force. The buckets descended empty, rose full, and discharged automatically. The system ran as long as the water wheel turned. Evans connected these mechanisms into a production line. Grain entered at ground level, moved horizontally via screw conveyor to the base of a bucket elevator, rose to the upper floor, traveled horizontally again to the millstones, then descended through chutes to the packing station. The entire process required human labor only to start the machinery and collect the finished flour. The economics were stunning. Evans reduced milling costs by 50%. A mill that once required a dozen workers could operate with 2 or 3. Production speeds doubled, then tripled. The automated mill represented the first true assembly line in American industry, decades before Henry Ford applied the same principles to automobiles. But the innovation remained dormant. Evans built his mills in the 1780s, but the supporting infrastructure did not exist. Steam power was experimental, and flour mills served local markets that did not need to process millions of bushels. The scale that would justify Evans's system had not arrived yet. His patents expired, and his designs gathered dust in technical journals. Evans died in 1819, never seeing his system transform American commerce. He had built the blueprint for the kinetic revolution, but it sat waiting for a problem big enough to demand it. That problem arrived 23 years later. And if you want to see more stories like this, hit that subscribe button, because you're going to want to find out how a merchant fixed America's biggest bottleneck. Joseph Dart was not an engineer. He was a merchant, a businessman who watched his profits evaporate in Buffalo's gridlocked harbor. In 1842, he owned grain, ships, and warehouses, but none of it mattered if the wheat could not move from hold to dock to canal boat before it rotted. Dart had read about Oliver Evans. He understood the principle: buckets on a belt powered by steam, lifting grain vertically without human muscle. But Evans had built for flour mills, processing hundreds of bushels. Buffalo needed to move thousands. Dart needed someone who could scale the concept to industrial dimensions. Robert Dunbar was that engineer. Together, they spent the winter of 1842 to 1843 constructing a facility unlike anything America had seen. It was a wooden structure, 50 by 100 feet, rising above the waterfront. Inside, a steam engine drove a continuous belt fitted with iron buckets. The marine leg extended down into the ship's hold. The bucket scooped grain directly from the cargo and lifted it 30 feet to storage bins above. The facility became operational on June 1, 1843. The first test run moved 600 bushels per hour, 10 times faster than the fastest stevedore crew. By the end of the first year, the system was handling 2,000 bushels per hour with mechanical precision that never tired, never slowed, never demanded wages. The economic transformation was immediate. What had taken a week now took hours. Ships that once waited days for an unloading berth could discharge their cargo and return to the lakes the same day. The bottleneck that had threatened to strangle Buffalo's commerce simply vanished. Other merchants watched Dart's elevator with the desperation of men watching their businesses die. Within 2 years, competing elevators rose along the waterfront. By 1860, Buffalo operated 10 major grain elevators with combined storage capacity exceeding 1.5 million bushels. The city that had nearly drowned in grain now processed it faster than the Midwest could grow it. The architectural impact matched the economic one. The grain elevator emerged as a new building type, tall, functional structures defined entirely by their mechanical purpose. Vertical storage bins were stacked like columns. The marine leg extended like an arm into the water, and there was the constant hum of steam engines. These were not warehouses. They were machines you could walk inside. By 1865, Buffalo operated 26 grain elevators. The city had surpassed London, Odessa, and Rotterdam to become the world's largest grain port, handling over 7 million barrels of wheat and flour annually. The Erie Canal had created the opportunity, but Dart's elevator made it real. The innovation changed more than throughput numbers. It changed the nature of the commodity itself. Grain was no longer measured in sacks, discrete, countable units that men carried. It was measured in volume, in bushels per hour, in the continuous flow of material through mechanical systems. The elevator did not just move grain faster, it transformed grain from a solid into a fluid, from something that sat in piles into something that streamed through pipes and chutes. Dart had solved the vertical problem. Grain could now rise from ship holds to storage bins without human intervention. But the horizontal challenge remained, moving grain across vast distances inside the elevators themselves, distributing it between storage bins and loading it onto rail cars and canal boats. The next innovation would not come from Buffalo. It would come from the mining industry, where another problem of bulk material handling was about to produce a solution that would reshape grain storage forever. DART's elevator had conquered height, but it had created a new problem. Grain rose vertically through bucket chains, but once it reached the top, gravity was the only force moving it horizontally. Storage bins had to cluster directly beneath discharge points. The footprint of the facility was limited by the physics of falling grain. The early grain elevators worked like vertical pipes. Grain went up, then came straight down. Moving it sideways meant shoveling it into carts, wheeling those carts across the floor, and dumping them into different bins. The elevator eliminated manual labor for vertical transport, but it left horizontal movement trapped in the 18th century. The mining industry solved it first. Thomas Robbins was developing ore handling systems for Thomas Edison's mill in Ogdensburg, New Jersey, when he invented the rubber-covered steel belt conveyor in 1892. Previous belt systems used animal leather, flexible but fragile, and prone to tearing under heavy loads. Robbins replaced leather with industrial rubber bonded to steel cables, creating belts that could carry tons of ore across hundreds of feet without breaking. The innovation was not just stronger materials. It was the system architecture: steel idler rollers supporting the belt at regular intervals, drive pulleys at each end, and the belt itself forming an endless loop. The conveyor could run horizontally at an incline or in complex paths around obstacles. It could be disassembled and relocated when mining operations moved to new sites. Most importantly, it was cheaper to maintain than rail cars and required no human operator once started. Grain elevator operators recognized the potential immediately. By the early 1900s, belt conveyors were threading through the interiors of Buffalo's elevators like horizontal highways. Grain no longer fell straight down from bucket elevators. It traveled across the building on rubber belts, could be diverted to any storage bin, and moved continuously without interruption. The architectural implications were profound. Elevators could expand horizontally, adding storage capacity without building taller. The first massive concrete terminals appeared in 1906, 14 years after Robbins's invention, rising like cathedrals on the plains. These were not just taller versions of DART's wooden structure. They were integrated systems where grain flowed through three-dimensional networks of belts and chutes, directed by operators who controlled gates and switches like railroad dispatchers. The belt conveyor completed the transformation DART had started. Grain moved vertically via buckets, horizontally via belts, and could be routed anywhere within the facility without human touch. The elevator became a machine for storing and sorting flowing material, not just lifting it. Railroads integrated directly with this infrastructure. Trains pulled alongside elevators, and grain flowed from storage bins down chutes into rail cars, the entire loading process controlled by mechanical gates. What had once required teams of workers shoveling grain into sacks now happened automatically, measured in tons per hour rather than sacks per day. The ports and terminals were fully mechanized. Buffalo, Chicago, Kansas City, the great grain hubs, operated like hydraulic systems, grain flowing through them like water through pipes. But back on the homestead, the farmer still owned a shovel. The year was 1945. Peter Pakosh stood in the basement of his Toronto home, watching grain slide through a metal tube powered by a rotating screw. The principle was ancient. Oliver Evans had used it in the 1780s, but Pakosh had made it portable. The war had ended. Soldiers were returning to farms across North America, facing the same back-breaking labor their grandfathers had endured. The industrial elevators in Buffalo and Chicago moved millions of bushels with mechanical precision, but the farmer with 200 acres still climbed into his wagon box with a shovel, moving grain one scoop at a time from truck to bin, bin to truck, truck to rail car. The back-breaking work of the shovel was the last lonely bottleneck. Every transfer cost hours of his life. Pakosh built a tube 16 feet long, fitted with a helical screw inside, powered by a small gasoline engine. The auger could be positioned at an angle, one end in a truck bed, the other reaching into a storage bin. Start the engine, and grain flowed upward at 1,200 bushels per hour. One man could move in an afternoon what used to take a crew all day. He took his prototype to Massey Harris, the largest farm equipment manufacturer in Canada. The head designer examined the machine, then delivered his verdict. As the auger aged and bent, metal on metal friction would start fires all across Canada. The company wanted nothing to do with it. Pakosh built them anyway. In 1945, he manufactured 10 units. Farmers who bought them told their neighbors. The next year, he built 50. Word spread through rural communities like a contagion. There was a machine that could eliminate the shovel. The versatile brand emerged from this basement operation. The auger was not elegant, but simplicity was the innovation. It was just a steel tube with a rotating screw, a simple bearing, and an engine mount. No complex gearing, no steam boilers, no elaborate belt systems. A farmer could afford it. A farmer could fix it. A farmer could operate it alone. The democratization was complete. The power that DART had given to terminal operators, Pakosh delivered to individual farmers. The grain elevator had industrialized the ports, but the portable auger industrialized the farmyard. Every homestead became its own mechanized handling facility, scaled to match its production. Abraham Plett saw the potential in 1951. He had been reselling Pakosh augers when one failed. The undercarriage could not handle the stress. Plett built a better frame, selected a bright yellow paint that echoed the color of ripe wheat, and founded Westfield. The iconic yellow auger became as common on the prairie as the grain it moved. By the 1960s, grain augers were standard equipment. Farmers who had spent entire seasons shoveling grain now positioned a tube, started an engine, and walked away while the machine worked. The labor that had consumed harvest season, the physical toll that had aged men before their time, simply vanished. The auger completed the chain DART had started. Grain flowed from field to combine to truck, truck to auger, auger to bin. Every link was mechanized. The shovel remained in the barn, a relic of an era when human muscle was the only force available to move the harvest. But the harvest itself, the combine cutting through fields, was still a stop-and-start affair. The machine that could thresh wheat faster than any crew still had to pause, dump its tank into bags or small bins, then resume cutting. The final bottleneck remained, the combine itself. The combine harvester of the 1940s was a marvel, a machine that could cut, thresh, and clean grain in a single pass through the field. But it carried a fatal flaw inherited from the manual era. It still required stopping. The grain tank held 100 bushels. When full, the operator shut down the header, climbed out of the cab, and waited for a truck to pull alongside. Then came the unloading, shoveling grain from the tank into sacks or dumping it through a small chute into the truck bed. The harvest paused while the combine sat idle, the afternoon sun burning away precious hours. Lyle Yost saw the absurdity in 1947. The combine could process acres per hour, but it spent one-third of its time parked, waiting to empty its tank. The bottleneck was not in the field, it was in the transfer. Yost mounted an auger directly onto the combine chassis, a tube extending from the grain tank powered by the machine's own engine. The Massey Harris Model 21 became the first production combine with integrated unloading. The grain tank still held 100 bushels, but now it could discharge while moving. A truck pulled alongside, matched the combine's speed, and the auger poured grain into the truck bed without either vehicle stopping. Skilled operators turned it into an art form. The combine never paused. The truck synchronized its path, staying parallel while the auger swung over and grain streamed into the bed. When the tank emptied, the truck peeled away to the bin while another took its position. The harvest became continuous, a flowing operation where the only limit was how fast the header could cut. This innovation didn't stop with Yost. Today, we have autonomous grain carts that synchronize wirelessly with the combine. Systems from companies like Raven Industries use radar and LiDAR to lock the tractor's speed and heading to the harvester, allowing the unloading auger to pour grain into the cart with millimeter precision without a driver in the tractor seat. It is the ultimate realization of the flow concept. The grain never stops moving. The kinetic revolution was complete. Evans had automated the mill. Dart had mechanized the port. Robbins had created horizontal transport. Redler had mastered the gentle flow. Pakosh had brought the technology to the farm. And Yost had closed the loop, integrating the harvest itself into the continuous flow. We stopped carrying the harvest the day we built a riverbed of steel for it to flow through. American abundance was unlocked not just by growing more, but by moving it faster, turning friction into flow, burden into current. Today, sensors and automation refine what Evans, Dart, and Pakosh built, but the revolution they started is complete. The true legacy is not the technology. It is the steady hiss of the auger, the sound of a harvest that has finally outpaced the shovel. It is the whoosh of thousands of bushels being forced up the tube, leaving the heavy lifting to the steel. Subscribe so you won't miss on future stories like this.